Welcome back to the deep dive. Today we are doing something that I honestly think we don't do enough of. We're turning the spotlight inward.
Mm.
Or, to be a little more accurate, we're turning it downward. We are going to deconstruct the structural engineering of your own lower body.
It's a fascinating landscape.
Yeah.
We often move through the world completely oblivious to the machinery that's, well, right underneath us.
Right.
We take our legs for granted until they hurt. But when you actually stop and look at the blueprint, the bones, the ridges, the connection points, it's just a marvel of biological architecture. It's not just biology, it's physics.
Exactly. And I want to set the boundaries for everyone listening right at the start because the source material is very specific today.
It is.
When we say leg in this deep dive, we are being anatomically precise. We are not talking about the thigh. We are not talking about the femur.
No.
We are strictly talking about the region from the knee down to the foot.
That is such a crucial distinction. In casual conversation, you say, my leg hurts, and you might mean your quad, right?
Yeah, of course.
But in anatomy, the leg is strictly the tibia and the fibula. Everything above the knee is the thigh.
So our mission today is to unpack those two bones, the tibia and the fibula, and then move down into the complex machinery of the foot.
Oh, the foot.
And looking at the notes, the foot is where things get really wild. 26 bones.
26. It's a masterpiece of segmentation. You have to think about the design challenge there.
Okay.
You need rigidity for leverage, so you can push off the ground, but you also need flexibility for balance, so you don't topple over on uneven terrain.
Two opposite requirements.
Completely opposite. And the only way to solve that engineering problem is with a lot of small interlocking parts.
And what really struck me in reading the source material is that we tend to visualize bones as these smooth, static white sticks.
The cartoon bone.
Yeah, the cartoon bone a dog chews on. But these documents paint a picture of a dynamic, almost, violent landscape. There are ridges and notches and holes and rough patches everywhere.
Precisely. And this is the key to understanding anatomy. Every one of those rough patches or lines tells a story of force. They are not imperfections, they are specific coordinates.
Coordinates for what?
They're where muscles grip the bone to create movement, or where ligaments attach to provide stability. If the bone were perfectly smooth, you wouldn't be able to walk.
So the muscles actually shape the bone.
The bone literally shapes itself in response to the pulling of your muscles. It's incredible.
So let's meet the dynamic duo of the lower leg. We have the tibia and the fibula.
The tibia is the heavyweight. It's on the medial side.
That's the inside of your leg.
Right, the inside. It is the weight bearer. When you stand up, the massive force of your body weight is traveling almost exclusively through the tibia.
And then there's the fibula. It's on the lateral side, the outside.
Yes.
And looking at the diagram, it looks kind of spindly compared to the tibia.
It does.
It almost looks like an afterthought.
It is much thinner, yes. And that raises a question I often hear, which is, why do we have two bones in the lower leg when the thigh only has one massive femur?
Yeah, why not just have one giant shin bone?
Right.
I was wondering that myself. It seems redundant to have a skinny bone right next to a fat one.
It's not redundant. It's all about the difference between support and stability. The femur is about raw power and support.
Mm-hmm.
But the lower leg needs to facilitate complex rotation and, crucially, stability at the ankle. The fibula acts as a lateral stabilizer. I like to think of it like an outrigger on a canoe.
An outrigger. Explain that.
Well, if you have a narrow canoe, it's tippy, right? It can roll over. Right. But if you attach a pole to the side, an outrigger, you stabilize the whole vessel without adding much weight.
Okay.
The fibula doesn't carry the main load of your body, but it provides a massive surface area for muscle attachments.
Yeah.
And as we will see, it locks the ankle in place so you don't roll your foot every time you step on a pebble.
Okay, that makes a lot more sense now. Let's unpack this properly. We're going to start at the top, just below the knee, and work our way down. Let's look at the tibia first, the shin bone.
The tibia, as we said, it's the weight bearer. If you look at the proximal end, that's the top part that meets the knee, it is huge. It flares out to create this wide platform.
These are the condyles, right?
Correct. You have the medial condyle and the lateral condyle. Think of them as the foundation pillars. They are these expanded surfaces that receive the condyles of the femur.
So it's a transfer station.
It's a transfer station, passing the weight from the thigh down into the leg.
The notes mention that these surfaces are slightly concave, like a shallow dish.
They are. They act like shallow saucers for the rounded ends of the femur to sit in. But, and this is really important, they are relatively flat.
Okay.
This is why the knee is such a tricky joint. It's not a deep ball and socket like your hip, which is inherently stable. It's like round rollers sitting on a flat table.
That sounds incredibly unstable.
Structurally, it is. That's why the soft tissue and the specific bony attachments we are about to discuss are so incredibly critical. The bone has to provide anchor points to keep that unstable table from just sliding apart.
Let's talk about those anchors then. The source material specifies some very particular muscle attachments on these condyles.
Right, so let's look at the medial condyle first. That's the inner side of the knee. On the posterior aspect, the back, there's a groove for the attachment of the semimembranosus muscle.
That's one of the hamstrings, right?
Correct. It's one of the big muscles on the back of your thigh. Now, think about the physics here.
Okay.
The semimembranosus runs down the back of the thigh, and it grabs onto the back of the medial tibial condyle. When it contracts, it pulls that back edge of the tibia up towards your butt.
Creating flexion, bending the knee.
It's pulling the lever, exactly.
So what about the other side?
Now, jump over to the lateral condyle, the outside of the knee. Here, you have the attachment for the biceps femoris muscle.
The other hamstring.
The biceps of the leg, yeah.
Yeah.
But here is the interesting thing. The biceps femoris doesn't just attach to the tibia. It also splits and grabs the head of the fibula, which we'll see later.
Oh, just
It's a dual insertion muscle, which helps bind the two leg bones together right at the top.
Now, sitting right between these two condyles, these two saucers, there is a structure that sounds very impressive, the intercondylar eminence.
The eminence, it sounds regal, doesn't it?
It does, but looking at it in the diagram, it just looks like a jagged little mountain range in the middle of the bone.
That is a perfect description. It is an elevation, a bumpy ridge rising up between the two smooth articular surfaces. And while it looks rough, this is arguably the most critical square inch of bone for knee stability.
Why is that? Why is this little bump so important?
Because it serves as the anchor point for the internal safety belts of the knee. This is where the anterior cruciate ligament,
The ACL.
the ACL, and the posterior cruciate ligament, the PCL, attach.
Oh, wow. So when we hear about athletes tearing an ACL, this is literally the jagged piece of bone where that ligament was holding on.
Exactly. The ACL attaches to the anterior part of this eminence, and the PCL attaches to the posterior part. Think about what they do.
They stop the sliding.
Right. The ACL stops the tibia from sliding forward out from under the femur. The PCL stops it from sliding backward. They are cross-braced ropes, and the intercondylar eminence is the stake in the ground they are tied to.
That puts a lot of context into that small bump of bone. It's taking a huge amount of shear force.
A huge amount of force, and not just ligaments.
Yeah.
The central tips of the medial and lateral menisci, those C-shaped shock-absorbing pads in your knee,
Yeah.
they also tether to this intercondylar eminence. Without that bony elevation to anchor them, the menisci would just slide out the sides of your knee every time you jumped.
That is a terrifying image.
It's not a good day when that happens.
Okay, moving just slightly down from there. On the front of the tibia, we have the tibial tuberosity.
You can actually feel this on yourself right now. If you were sitting down, put your hand on your kneecap.
Okay.
Now slide your finger down about an inch or two. You feel that hard, prominent bump at the top of your shin.
Yeah, I can feel that. It's pretty hard. It really juts out.
That is the tibial tuberosity.
And what is its job? What's its purpose?
Its sole purpose is to be the attachment point for the patellar ligament.
Okay, let's trace the mechanics of that for a second.
Sure. You have the quadriceps, the massive muscles on the front of your thigh. They all merge into a single tendon that engulfs the kneecap, the patella.
Right.
Then from the bottom of the kneecap, that tendon becomes the patellar ligament, and it attaches to this bump, the tibial tuberosity.
So it's a pulley system.
Precisely. The kneecap acts as a fulcrum, pushing the tendon away from the joint, and the tibial tuberosity is the handle that the muscle pulls on. When your quads contract, they pull the kneecap, which pulls the tuberosity, which levers your legs straight.
Yeah.
If that tuberosity were flush with the bone, if it didn't stick out, you would lose a huge amount of mechanical advantage.
You'd be weaker.
Much weaker extending your leg. It's basic leverage. You're increasing the distance from the pivot point.
It's physics and biology.
Always.
Okay, let's move down the shaft of the tibia. This is the part we mostly identify as the shin. And looking at the cross-section in the notes, it's not round.
Yeah.
It's triangular.
Correct. It had 3 surfaces and 3 borders. And this shape explains a lot about the common injuries we see.
I assume we're talking about why getting kicked in the shin hurts so much.
That is entirely due to the medial surface.
The interface of the triangle.
Right. The medial surface is what we call subcutaneous.
Subcutaneous.
There is no muscle covering it. It is just skin, a thin layer of fascia, and then the periosteum of the bone. That is why impact there is so painful. There is Absolutely no cushion. It's just bone-on object contact.
But even though it's exposed, it's not completely empty of attachments at the top, is it? I see something in the notes here.
No, you're right. At the very top of this medial surface, just below the knee, there is a famous convergence of tendons. The source mentions the aponeurosis derived from the tendons of the sartorius, the gracilis, and the semitendinosus.
That's a mouthful.
It is. In clinical terms, we call this the pes anserinus.
Descenserinus.
That is Latin for goose's foot,
Goose's foot. Why?
because of the shape. Imagine 3 tendons coming from different directions. The sartorius from the hip, the gracilis from the groin, and the semitendinosus from the back of the thigh. They all swoop down and attach at this one spot on the upper medial tibia, splaying out like the webbed foot of a goose.
So why do they all meet there? What's the point of that?
Stability. They were coming from 3 different angles to stabilize the medial side of the knee against twisting forces. It's like guide ropes on a tent.
Okay, so that's the medial side, the shin. What about the lateral surface? That's the side facing the fibula.
The lateral surface is protected. It's covered by the muscle bellies of the tibialis anterior, the extensor hallucis longus, and the extensor digitorum longus.
Those are the muscles on the front and side of the shin, right?
Yes. If you lift your toes up right now, pull your foot toward your shin, you can see and feel those muscles pop out.
Yeah, I can.
They use that concave lateral surface of the tibia as their origin point. They cling to the bone there, so they have something to pull against to lift the foot upward.
And shin splints.
This is the region involved in shin splints. Often it's the tibialis anterior muscle pulling too hard on its attachment to the bone, causing inflammation of that periosteum.
Now we have to talk about the posterior surface, the back of the shin bone. The source material gets really detailed here about something called the popliteal line or the soleal line.
This is a fascinating bit of topography.
Yeah.
I want you to visualize the back of the tibia. It's not smooth.
Okay.
There is a prominent oblique ridge running diagonally downward from the outside to the inside. That is the soleal line.
And it's there because it's a note, a muscle attaches to it.
Exactly. Because of the soleus muscle. The soleus is one of the 2 major calf muscles. It lies underneath the gastrocnemius. It is an absolute workhorse.
The workhorse of the calf.
It's responsible for keeping you upright. Every time you stand still, your body wants to fall forward due to gravity. The soleus is constantly pulling back on the tibia to keep you standing. It's an anti-gravity muscle.
That's always under tension.
Constant high-tension load. That muscle grips onto the back of the tibia so hard that over your lifetime, it literally raises this ridge of bone. The soleal line is essentially a scar of mechanical stress.
Wow.
It marks the boundary where the popliteus muscle, which unlocks the knee, sits above it, and the soleus and other flexors sit below it.
It's like a mountain range on the back of the bone that separates the different layers of calf muscles.
Exactly. And attaching along that same rough area are the flexor digitorum longus.
Which curls your toes.
Right, and the tibialis posterior. It's a very crowded, high-traffic area for muscle attachment.
And there's one more detail on the posterior surface that the notes highlighted. The nutrient foramen.
Yes. It sounds technical, but foramen just means hole. The nutrient foramen is a tunnel into the bone.
A tunnel.
A literal canal. This is where the nutrient artery dives inside the bone to supply blood to the marrow and the internal bony structure.
I think we often forget that bone is living tissue. It needs oxygen, it needs nutrients.
It bleeds, it heals, it remodels itself constantly, and it needs a dedicated plumbing system. The nutrient foramen is the main intake pipe for the tibia.
So if you break the bone.
If you break the bone in a way that shears off this artery, healing becomes much, much more difficult. The blood supply is compromised.
That's a crucial detail. Okay, so that's the shaft. Let's get to the bottom, the distal end.
This is where the tibia meets the ankle, and the most prominent feature here is the medial malleolus.
That's the big bump on the inside of your ankle.
Right. If you reach down and touch the inside of your ankle, that hard knob is the tibia. It acts as a bracket. It reaches down and cups the side of the talus bone of the foot. It forms the medial wall of the ankle joint.
So it prevents the foot from sliding inward.
Exactly. It creates a vertical wall to stop that motion.
And on the other side of that distal end, on the lateral side, the tibia doesn't have a bump. It has a notch.
The fibular notch. It does exactly what it says on the tin. It's a concave depression specifically shaped to receive the bottom of the fibula.
Why is this connection so important?
Because the ankle joint is a mortise. Do you know what a mortise and tenon joint is in woodworking?
It's like a slot and a tab, right? You fit one into the other.
Right. The ankle is the slot, or the mortise, formed by the tibia and fibula. The foot bone, the talus, is the tendon that fits inside that slot.
Okay, I see that.
For that slot to be stable, the tibia and fibula have to be strapped incredibly tightly together. The fibular notch is where they meet. Ligaments bind them there with immense strength.
And if they separate?
If they separate, what we call a high ankle sprain, the slot widens and the foot becomes unstable. The whole joint is compromised.
Which brings us perfectly to the partner in this operation, the fibula, the lateral stabilizer.
The fibula. As we noted, it is much slimmer. But let's clarify something structurally. The fibula does not articulate with the femur.
Wait, really? It doesn't touch the knee joint?
No, it stops just short. It connects to the side of the tibia, but it is excluded from the main weight-bearing hinge of the knee.
So if it's not carrying weight and it's not part of the knee, again, why is it there?
Muscle real estate and ankle stability. Let's look at the proximal end, the head of the fibula.
It's described as a small, knob-like extension.
It sits tucked under the backside of the tibial plateau. It articulates with that lateral condyle of the tibia we talked about. This is the proximal tibiofibular joint.
And looking at the list of attachments here, for such a small bone, it's incredibly crowded.
It is prime real estate. You have the soleus muscle attaching there. You have the biceps femoris. Remember I said that would come back?
Yes, the hamstring muscle.
It grabs the head of the fibula. This is vital. When your hamstring pulls, it's not just bending the knee, it's also stabilizing the outside of the joint by pulling on the fibula.
What else?
Then you have the fibularis longus, the extensor digitorum longus, and the fibular collateral ligament, or the LCL.
The LCL.
That ligament is the main strap preventing your knee from buckling outward. It runs from the femur down to the head of the fibula.
And there's a specific point mentioned called the styloid process?
Yes, the styloid process is a rough prominence extending upward from the head. Think of it as a hook.
A hook for what?
It gives the biceps, femoris tendon, and the LCL a mechanical lip to grind onto so they don't slip off under high tension. It provides a more secure anchor.
Now let's move down the shaft of the fibula. The source material describes this in terms of borders, and honestly, reading it felt like looking at a game of Tetris.
It's a great analogy.
You have borders creating partitions for different muscle groups.
It creates a compartment system.
Yeah.
That is the best way to visualize the lower leg. It's packed tight. The fibula is deep inside, surrounded by muscles. Its very shape is defined by the walls, the septa that separate those muscles.
So let's break down these borders. We have the anterolateral border.
This border acts as a fence. It separates the extensor muscles on the front of the leg.
The ones that lift the foot.
Right. It separates them from the peroneus muscles or fibularis muscles on the side.
The ones that turn the foot out.
Exactly. And attached to this border is the intermuscular septum, literally a tough wall of fascia that keeps those muscle groups in their own lanes.
Then we have the anteromedial border, also called the interosseous crest. This one seems really important.
This is arguably the most critical border structurally. Interosseous literally means between bones.
Right.
This crest is the attachment point for the interosseous membrane.
We need to spend a minute on this membrane. It's not just a wrapper, is it?
Yeah. No, absolutely not. Imagine a thick, fibrous sheet, almost like a sail or a piece of canvas, stretching tightly between the tibia and the fibula. It runs almost the entire length of the leg.
What is its function? What does it do?
It's a suspension bridge system.
Yeah.
It does two main things. First, it binds the bones together so they don't splay apart under load. It makes them a single unit.
And second?
And second, and this is more interesting, it transfers force. When you step, the force goes up your foot. Most of it goes into the tibia, but some of that force is transferred from the tibia across the membrane to the fibula.
So it helps distribute the load.
It allows the two bones to share the stress. So the fibula isn't just floating there. It's tied to the tibia by this high-tension sheet along that specific crest. It also acts as a divider, separating the muscles in the front compartment from the deep muscles in the back compartment.
And then you have the posteromedial border or the oblique line.
And again, it's about partitioning. This one separates the tibialis posterior muscle from the soleus and the flexor hallucis longus. The bone is twisted and shaped by the need to pack all these different motors into a very small space.
Okay, let's get to the bottom of the fibula, the distal end. This is the lateral malleolus.
If you touch the outside of your ankle, that hard bump is the lateral malleolus. Now, I want you to do something.
Okay.
Put one hand on your inner ankle bone, the medial malleolus, and one on your outer ankle bone, the lateral malleolus. Compare their height.
Okay. Huh. The outside one, the lateral one, it definitely feels lower. It projects down further.
It is. The fibula extends further down in the tibia.
Why? What's the advantage of that?
It acts as a doorstop. Because it hangs lower, It creates a rigid, bony wall on the outside of the ankle joint. This physically prevents your foot from rolling outward, what we call eversion, too easily. It creates a locking mechanism for the talus bone.
So if I land awkwardly, that bone physically blocks the foot from sliding sideways.
Exactly. And looking at the attachments here, it's all about holding the foot on. You have the calcaneofibular ligament and the anterior and posterior talofibular ligaments,
The ATF ligament, that's the one everyone sprains.
the most common sprain in the body. When you roll your ankle inward, you are stretching or tearing the ligament that connects this fibular bone, the lateral malleolus, to the foot. The bone is the anchor, the ligament is the rope. When the rope snaps, you have a sprain.
So we've talked about the two bones separately, but as you mentioned, they are a system. Let's look at part 3, the joints and articulations.
They really do work in concert.
Up top, we have the proximal tibiofibular joint.
That's a synovial joint formed by the lateral tibial condyle and the head of the fibula. Now, interesting fact, this joint allows a tiny amount of gliding movement.
Why does it need to glide? It seems like you'd want it to be solid.
You would think, but the ankle changes shape slightly as you move your foot up and down, and the fibula needs to be able to adjust its position slightly to accommodate that. If this top joint were fused solid, your ankle range of motion will be restricted. It needs that little bit of give to absorb the twisting forces coming up from the ankle and down from the knee.
And at the bottom, the distal tibiofibular joint.
This is formed by that fibular notch on the tibia gripping the fibula. This joint is much, much stiffer. It has to be. It's a fibrous joint, a syndesmosis.
Is the bracket.
It forms the bracket that sits on top of the foot. If this joint spreads apart, that high ankle sprain we mentioned, the talus will wobble around inside the joint space, destroying the cartilage.
So to recap the connections to the rest of the body, proximally, the tibia meets the femur at the knee.
Right.
Distally, both bones meet the talus.
That is the ankle joint proper, the talocrural joint. You have the tibia sitting on top, the medial malleolus cupping the inside, and the fibula's lateral malleolus cupping the outside. It grabs the talus like a wrench gripping a nut.
Which is the perfect transition to part 4, the foot. And this is where I really want to slow down and dig in because the complexity here is just mind-boggling.
It's an engineering marvel.
26 bones. That is a lot of hardware in such a small space. Why do we need so many pieces?
Think about what the foot has to do. It has a completely contradictory job description.
Okay.
When you land a jump, it needs to be a loose bag of bones to absorb shock, to splay out and dampen the impact. But a split second later, when you push off to run, it needs to turn into a rigid, solid lever.
So it has to be both rigid and flexible at the same time.
Exactly. And you can't do that with one solid block of bone. You need a chain of bones that can lock and unlock. That's why we have 26 of them.
Let's break them down. We have the tarsals, the metatarsals, and the phalanges. Let's start with the tarsals. There are 7 of them, forming the back half of the foot.
These are the heavy-duty bones, a foundation.
And the king of the tarsals seems to be the talus.
The keystone. The talus is the most superior tarsal. It is the connector. It is the only bone in the foot that articulates directly with the leg bones, with the tibia and fibula.
But here's something weird I read in the notes. The talus has no muscle attachments. None at all.
That is the most unique and important thing about it. No muscles attached to the talus.
Yeah.
Not a single one.
So how does it move?
It is moved entirely by the forces of the bones around it. It is essentially a ball bearing. It's trapped between the leg bones above and the heel bone below. It distributes the weight and allows the foot to pivot, but it is entirely passive.
So it's vulnerable.
Very vulnerable to blood supply issues if it breaks, because there are no muscles bringing blood vessels directly into it.
That is fascinating. It's a floating joint interface.
Exactly, and it sits on top of the calcaneus.
The heel bone, the calcaneus.
The largest tarsal bone. This is the bone that hits the ground first. It is built like a tank. It has to withstand the impact of your heel strike every time you take a step, which can be multiples of your body weight.
And looking at the structure, it projects backward, behind the ankle joint.
That backward projection is a lever arm. The Achilles tendon attaches to the back of the calcaneus. Because the bone sticks out backward when the calf muscle pulls up on it, it has tremendous leverage to push the front of the foot down.
It's the same physics as the kneecap.
The same principle as the tibial tuberosity, just at the ankle. It's all about mechanical advantage.
The notes also mention that the calcaneus participates in both the medial and lateral longitudinal arches.
It is the posterior pillar. All the arches of the foot begin at the calcaneus. It's the starting point for the whole structure.
Okay, moving forward from those two giants, on the medial side, the big toe side, we have the navicular.
The boat-shaped bone. It sits in front of the talus. It acts as the keystone of the medial longitudinal arch.
The keystone.
If you look at an X-ray of a high-arched foot, the navicular is sitting right at the peak of the curve. It's the central stone that holds the arch up.
And on the lateral side, the little toe side, we have the cuboid.
It is roughly cube-shaped, as the name implies. It sits in front of the calcaneus, and it lies proximal to the fourth and fifth metatarsals.
Does it act differently than the navicular?
Yes. The cuboid is part of the locking mechanism of the foot. There is a groove on the bottom of the cuboid where the peroneus longus tendon runs.
So a tendon runs underneath it.
It runs underneath and across the foot. The groove on the cuboid acts like a pulley, redirecting the force of that muscle across the bottom of the foot to help support the arches.
And then we have a trio of bones called the cuneiforms.
The three wedges. You have the medial, intermediate, and lateral cuneiforms. They sit just proximal to the first, second, and third metatarsals.
I love the name cuneiform. It means wedge-shaped, right?
Yes, like the ancient writing system.
Yeah.
But structurally, this is brilliant. Think about a Roman stone archway. To make the curve, the stones at the top have to be wider on the top than they are on the bottom.
So they don't fall through. It creates a self-locking structure.
Exactly. The cuneiform bones are physically shaped like wedges. They are wider on the dorsal, or top, surface, and narrower on the plantar, or bottom surface.
So the bones themselves force the foot into an arch shape?
Yes. Even if you stripped away all the muscles and ligaments, these bones would naturally form a curved ceiling because of their intrinsic shape. It's structural masonry inside your foot.
And what arch do they form?
They form the transverse arch, the curve that goes across your foot from side to side.
So flat feet aren't just lazy muscles. It can be a structural difference in the shape of these wedges.
Absolutely. If those wedges are more rectangular than wedge-shaped by genetics or injury, the arch collapses. It's a bony issue.
That covers the back end of the foot. Now we move to the metatarsals, the body of the foot.
Numbered I to V, from medial to lateral. So metatarsal I is behind the big toe. Metatarsal V is behind the little toe.
These look like miniature long bones.
They are. They have a base at the proximal end, a shaft, and a head at the distal end. The bases articulate with those tarsals we just met, the three cuneiforms and the cuboid. The heads articulate with the toes.
Is there a significant difference between them?
The first metatarsal, the one for the big toe, is massive compared to the others. It's short and thick because it takes the brunt of the push-off phase of walking.
And the fifth.
But look at the fifth metatarsal, the little toe one. It has a xyloid process at its base that sticks out to the side.
I can feel that bump on the outside of my foot halfway down.
That is the base of the fifth metatarsal. It's a very common fracture site, the Jones fracture.
Why there?
Because the peroneus brevis muscle attaches there. If you roll your ankle violently, the muscle can contract so hard it rips that piece of bone right off.
Ouch. And finally, we have the phalanges, the toes.
14 bones in total.
Wait, if we have 5 toes, shouldn't there be 15? 3 for each toe.
Ah, the exception. It's the same as the thumb in your hand. The hallux, the big toe, only has 2 phalanges, a proximal and a distal.
Why only 2?
It's shorter and stouter for power and stability during push-off. It's more of a rigid strut.
Okay, that makes sense.
But toes 2 through 5 have 3. Proximal, middle, and distal. That is why your big toe has 1 hinge, but your other toes can curl in 2 places.
It's the rule of 3 with 1 exception.
Exactly. And while they seem small and insignificant, they are vital for balance. They press into the ground to fine-tune your stability when you shift your weight.
So, putting this all together, we have traced the path from the knee all the way down.
Think about the journey of force. We started at the broad, weight-bearing condyles of the tibia, receiving the load from the femur. We saw the intercondylar eminence holding the knee together against those powerful shear forces.
We traveled down the triangular shaft of the tibia, seeing how the borders separate the muscles. We saw the soleal line literally scarred by the effort of standing upright.
We saw the fibula acting as the lateral outrigger, tied to the tibia by the high-tension interosseous membrane, stabilizing the whole column.
And we saw how they lock into the pallus, that perfect ball bearing, transferring all that weight into the calcaneus, and then spreading it out through the wedge-shaped cuneiforms and the arches.
That really emphasizes that so what question. Why care about a fibula notch or a soleal line?
Yeah, why?
Because form follows function. Those notches and lines are the blueprint of movement. The soleal line exists because the soleus muscle needs to pull firmly to let you stand. The fibular notch exists to stabilize the ankle so you can walk on uneven ground without breaking your leg. You are literally looking at the coordinates of human locomotion.
And here's a thought to leave you with, something that really stuck out to me in the source material, but we didn't fully dwell on: the arches.
The architecture of the stance.
We mentioned 3 arches: medial longitudinal, lateral longitudinal, and transverse. And we listed which bones go into which. But stop and think for a second. Why does the foot need 3 different architectural arches just to stand up? Most bridges only have 1 arch.
It is a provocative question. It seems overly complex.
It does, and it implies that standing isn't a passive act. If we had 1 arch, we could only handle force in one direction. But we have 3. It's a dynamic balancing act between 3 different curves, managing weight in 3 different dimensions simultaneously.
It creates a dome. A dome is infinitely stronger than a simple arch. By having 3 arches, your foot essentially creates a spring-loaded dome that can handle force from any angle forward, backward, or sideways. It leaves you thinking about the sheer engineering required just to stand still.
And realizing that every single one of those 26 bones has to be in the right place working with the others for that system to work. It is humbling.
Humbling indeed.
Well, look down at your feet with a little more respect today, folks. They are doing a lot of math down there. Thanks for listening to this deep dive into the anatomy of the leg and foot.
Keep learning.
See you next time.